Before we had the periodic table, before we had labs that look anything like they do today, chemistry was, well, it was kind of just chaos. So, how did we get from pure guesswork to a precise science? It happened by cracking a fundamental chemical code. And in this explainer, we're going to break down the 5 key laws that brought order to the entire world of matter. For hundreds of years, chemistry was like the Wild West. You had early scientists watching wood burn and turn to ash, or iron turning into rust, but there was no rulebook, none. It was just a random collection of observations. Matter seemed to just vanish into thin air, and reactions were totally unpredictable. It was, to put it mildly, a scientific mess. So the big question hanging over everything was pretty obvious. How in the world do we find the hidden rules that are governing all of this? This turned into a full-blown scientific detective story, a quest to uncover the fundamental laws of how chemicals combine. So, our investigation is going to follow 5 key clues that, piece by piece, built the foundation of all modern chemistry. We'll kick things off with conserving mass, then look at fixed recipes, decode the secret rules of gases, and finally see how it all comes together in the atomic blueprint, and maybe most importantly, why these laws still matter so much today. Okay, let's dive into our first mystery. Think about it. You burn a big log in a fire, and the pile of ash you're left with is way, way lighter than the log you started with. So where did all that other stuff go? Did the mass just poof, vanish? For early chemists, this was a huge, huge puzzle. This one simple statement, this was the breakthrough. It's the law of conservation of mass, and it was an absolute game changer. It basically meant that in any reaction, everything has to be accounted for. Nothing, and I mean nothing, is ever truly lost. And the detective who gets the credit for cracking this first case is the French chemist Antoine Lavoisier. He conducted these incredibly precise experiments and proved that the missing mass from that burning log wasn't gone at all. It had just turned into gases, like smoke and carbon dioxide, that escaped into the air. And this simple little equation right here shows you the proof. The law says that the total mass of the stuff you start with, we call those the reactants, has to equal the total mass of what you end up with, the products. So look at that example. 2 grams of hydrogen plus 16 grams of oxygen gives you exactly 18 grams of water. Mass is perfectly conserved. And just like that, clue number 1, solved. Okay, so mass is conserved. We've got that. But is that it? Do elements just combine in any old way they want? Or is there some kind of specific recipe? Could you make water with, say, just a little bit of hydrogen and a whole ton of oxygen? Well, it's time for our second clue. So enter the French chemist Joseph Proust and his law of definite proportions. Honestly, the most important word to focus on here is fixed. Proust found out that every single pure chemical compound has a strict, unchangeable recipe that's based entirely on the mass of its ingredients. And water is the perfect example. It doesn't matter where you get it from. An iceberg, a cloud, a lab experiment, pure H2O will always have a mass ratio of about 1 part hydrogen to 8 parts oxygen. That recipe is totally universal and completely non-negotiable. But of course, things get a little more interesting. What happens when 2 elements can form more than one kind of compound, like carbon and oxygen do? Well, an English chemist named John Dalton found the next clue. He figured out that even when this happens, there's still a simple, really elegant mathematical rule that connects them. Okay, now this table shows Dalton's law in action, and it's just brilliant. Let's break it down. We've fixed the mass of carbon at 12 grams for both compounds. In carbon monoxide, or CO, that 12 grams of carbon combines with 16 grams of oxygen. But in carbon dioxide, CO2, it combines with 32 grams of oxygen. Now, just compare the masses of the oxygen, 16 grams to 32 grams. What's that ratio? It's a simple, clean, whole number ratio of 1 to 2. That's the law. Beautifully simple, right? So far, all our clues have been about mass. But what about gases? They behave totally differently, and their volumes presented a whole new set of puzzles for our scientific detectives to figure out. So Joseph Gay-Lussac discovered something really fascinating. He found that when gases react with each other, their volumes also combine in these simple whole number ratios. For example, exactly 1 volume of nitrogen gas reacts with exactly 3 volumes of hydrogen gas, and what do you get? 2 volumes of ammonia gas. The ratio is a perfect 1 to 3 to 2. And this is where the Italian scientist Amedeo Avogadro has his big aha moment. He asked the question, why are the volume ratios so simple and clean? And he proposed a really radical idea for the time. What if it's because equal volumes of any gas, as long as they're at the same temperature and pressure, contain the exact same number of particles or molecules? This was the key that unlocked everything. It linked the visible volume of a gas to the invisible number of molecules inside it. So let's make sure we're totally clear on the difference here. Gay-Lussac was the observer. He was the guy in the lab measuring the volumes and seeing these simple ratios. But Avogadro was the theorist. He's the one who explained why it was happening. He figured out that the 1:3 volume ratio in our ammonia example exists because we're really talking about 1 molecule of nitrogen reacting with 3 molecules of hydrogen. All right, we've gathered all of our clues. We know mass is conserved, compounds have fixed recipes by mass, and gases react in simple ratios by volume. So now it's finally time to see how John Dalton connected all these dots to solve the case once and for all. I mean, just look at this timeline for a second. In a little over 20 years, from Lavoisier in 1789 all the way to Avogadro in 1811, each one of these discoveries built directly on the last one. You can literally see science marching forward, from complete mystery to the very edge of a revolutionary new understanding of matter itself. And here it is, the solution. Dalton's atomic theory. He proposed that all matter is made of these tiny, indivisible particles called atoms. And this one powerful idea explains everything we've just seen. Why is mass conserved? Well, it's because chemical reactions just rearrange these atoms. They won't destroy them. Why do the laws of proportions work? Because compounds are formed when these atoms combine in simple, fixed, whole number ratios. It all just clicked together. The case was cracked. So, okay, we've solved our historical mystery, but you might be wondering, why do these really old laws still matter to us today? Well, because they aren't just museum pieces. They are the absolute unshakable bedrock of all modern chemistry. These 5 laws are the foundation of a field called stoichiometry. I know, it's a fancy word, but all it really means is the math that runs all of chemistry. Stoichiometry lets chemists calculate exactly how much of one ingredient they need to react with another and predict exactly how much stuff they're going to get at the end. Every single time a new medicine is developed or a new material is created, it's all built on these fundamental rules. So these fundamental laws took chemistry from total chaos to crystal clarity. They cracked the first great chemical code and revealed the atomic blueprint of our entire universe. And it kind of makes you wonder, as we look to the frontiers of science today, whether it's in genetics or quantum physics, what's the next great code that's just waiting to be cracked?